There are several reasons to approach bioinformatics data processing using bash scripting. First of all, it allows the efficient processing of large biological data sets, and your methods are documented directly in the script. The script makes it easy to repeat the experiment. It's also easy to modify the script for the next data set. To begin bash scripting, start with the terminal and the appropriate operating system. Some may prefer Ubuntu. For others, it might be CentOS. My preference is to work from a Windows machine and shell into my Linux servers. In all of these cases, notice that a minimum of 3 terminals are open to allow for efficient programming. One to edit and save, one to test, and one to gather information for the next step. Now we'll look at the data that we're interested in. It's important we know the disease class for each data set that we download, and we have that information here. Also notice that we have a link to download the FASTQ files. For this example, at the bottom of the table, there's also a link that allows us to download this table in tab delimited format. So I've downloaded it. And I'm only showing it in a spreadsheet here to illustrate that we have the links we need to download the FASTQ files, as well as a disease class on the same line. So we have everything we need to download and tag these FASTQ files with the appropriate disease class. I know I'm going to need a loop of some kind to do this, so I'm going to start by showing a for loop in bash scripting. In this example, n is the variable, and it goes from 1 to 5. If I write and save this script using an editor, I can run it by calling bash on the command line with the name of the script, like this. With the ls command, I can see the file permissions. And I can change the file permissions to executable for this script like this. So when I check the ls command again, I can see that reflected in the file permissions. I can now run the script like this. Here's a for loop in another format. Notice also the comment line here, and below the comment line is the exit command. Nothing is executed after the exit command. This demonstrates that we can retain code chunks without having them executed when we run the script next time. In this example, I'm looping over a discrete set. When I run this code, I get this output. Here I'm setting the discrete set to a variable. When I run this code, I get identical output. In both cases, the for loop is parsing on the white space. Now imagine we have a data file like this. I'm using the cat command to display the content. I can also embed the cat command within the for loop. When I run it, I get results like this. Now imagine we have a data file like this, where we have data chunks with a space in between. If we run the for loop the same way, we get these results. In this case, the for loop is parsing on both the white space and the new line character. If we wanted to retain this data on the same line, the same way we see it in the file, we would use a while loop. When we run the while loop, we see that it's retained on the same line. Now let's return to the data we want to process. The tab delimited data is held in the text file that I've downloaded. I'm using the grep command to extract all the lines that contain the string fastq.gz. This is essentially all the lines with the exception of the header on the first line. The vertical bar here is called a pipe. I'm piping the output of the grep command to the head command. I've set head to pass only the first 2 lines from the input data stream and pipe those to the awk command. The awk command parses each line by white space, for example, a tab or a space character. It passes only the fields listed by number in the print statement. Also notice that I've set the print statement to output data in comma delimited format. The greater than sign is called a redirect. I'm redirecting the output of the awk command to a CSV file. I call this slicing and dicing. I'm taking slices of the file, then dicing out specific columns. The next line is commented out. It is the same as the above, but without the head command. After testing is completed, I'll use it to later download and process the entire data set. Using the cat command, you can see that for now, there are only 2 lines in the CSV file. Now we begin the edit and test phase. Our data is in comma delimited format, without white space, so we can use a for loop. Here the cat command is embedded in the for loop. I'm looping over the file, printing the first line, then exiting. We see the expected result. Now we're ready for more slicing and dicing. Here I'm echoing the line variable through the pipe to the cut command. D is for delimiter, in this case the comma. F is for field, in this case the first field. The output of the cut command goes to the variable. This is repeated for all the fields, putting them in the appropriate variables. The variable link contains the FTP file name. The base name command essentially lops off everything before the file name. If we use base name again, adding the .gz, it returns the file name without the .gz. Next, we build a new variable called newID. Running the script demonstrates that we have all the variables we want. Here's why we want these variables. I'm using the wget command on the link variable to download the FASTQ files. After the file is downloaded, the script runs the next line and unzips the file. After unzipping, the move command moves the file to the target directory. We need the link variable to download the FASTQ files. We need the file variable because it is the name of the file after downloading. After unzipping the file, the .gz is lost, so we need the stem variable. The new ID variable holds a disease class and the ID. Combined with the stem makes the complete file name. This is all wrapped in an if statement. It starts with if and ends with finish if. The bracket is a test case. F is for file exist. Combined with the exclamation point, it means if the file doesn't exist, then run this code block. This is helpful for testing, especially for large processes like downloading and unzipping large files. This way it is not repeated if it is already run. After running this script, we now have FASTQ files for processing. One of the first things one might do is to trim the sequences based on quality score. The FASTQ quality trimmer program is used in this example. Here I loop over the set of FASTQ files using the wildcard to process each one in turn. We know that the file extension is .fastq, so we use it with the base name command to get the file stem. Here are the command line parameters. I is for input file, O is for the output file. We needed the stem variable to set the output file name. The program called FastQC is used to document the quality of the sequence data, in this case performed after trimming. Unlike the FastQ quality trimmer program installed on the system, FastQC was downloaded and placed in a directory in my user account. It is not in the path, so I made a variable pointing to the full path of the application. FastQC creates a new directory for each file it processes. The program is called here, requires the path to create the directory. This is set using the -O. We need the stem variable to test if the output directory already exists. Here's the file to be processed. In this test case, D is for directory. If the directory exists, it returns a true condition. The double bars are an OR. It tests to see if one or the other statement equates to true. If the directory exists, then the OR is satisfied and does not run the make directory command. If we create a directory that already exists, we would get a warning. There's no problem with the warning. This method just avoids unnecessary output, while ensuring that the directory is always present when needed. These sequence data are of the type called paired end. The file names are designated as 1 and 2. Often these are processed together in pairs, with the results written to a single file. Here's how I approach that. I loop over the set of FASTQ files for only those designated as file 1 of the pair. The variable name is file 1. I get the stem name by piping the output of base name to the sed command. Sed is a stream editor. In this example, I'm replacing _1 with nothing. If I echo the variable file 1 through the pipe to the sed command, I can replace _1 dot with _2 dot and put that in the variable called file 2. The ls command demonstrates that I have both files in variables. Now we can bring it all together in a pipeline script. Notice that I can set the run status 2 ways. If I set the status to do and run the script, it starts executing lines here. If I set the run status to done, it begins processing after the finish if statement. If I move the finish if below the first for loop block, it would not execute that block on the next run. This way I can rerun any code block in the middle of the script. I can also place an exit to stop executing anywhere I want. This provides flexibility for testing. After the script is fully tested, it can be run in the background like this. No hup stands for no hangup. It means I can log off the system and the program will not terminate. With no hangup on the front end and the ampersand on the back end, the script will run in the background. In this example, I've redirected the output to a log file. I can check the log file for errors while running or after completion. When I press enter, I get the process ID. Hit enter again and it tells me that errors will be redirected to standard out, in this case the log file. Here the exit command closes the terminal connection. I could shut down my computer and go to bed if I wanted. My script is running on the server. Now to recap. I've demonstrated that bash scripting allows for the efficient processing of large data sets. I've also shown that the methods are documented in the script. For example, what parameters were used when running the FASTQ quality trimmer program? The parameters are documented here. It's easy to repeat the experiment. We can even repeat specific sections without repeating others if needed. And finally, the script is easy to modify for a different data set. The script can be copied to another location, and it will create the directory structure to hold the new results. I can also point the for loop to a different data set, then run the script. This concludes the tutorial on bash scripting for bioinformatics. Thank you.